Let's get started on your day 3 notes over inverse functions. We're going to be looking at more involved functions, cubic and cube root functions, exponential and logarithmic, and rational functions. So I should not have that there. So let's first get started on your cubic and cube root inverse functions. Cubic and cube root functions are inverse functions. We're going to prove this by finding the inverse of this cubic parent function below. Then we'll graph the function and its inverse on the graph provided. So let's first graph f of x equals x cubed on this graph provided. So that's your parent cubic function. I'm going to zoom in here, and it looks like this. It's going to take this shape right here. It goes to the origin. I didn't do that very well, but this is f of x equals x cubed. And as you can see, it is a one-to-one function. We know that because if we were to perform the horizontal line test, the horizontal lines only pass through one point. Therefore, it passes the horizontal line test. Therefore, this is a one-to-one function. And let's write that down. This is a one-to-one function, which means there are no domain restrictions. So as you recall, yesterday, day 2, we had domain restrictions. This is a one-to-one function, therefore there are no domain restrictions. We know the inverse will be a function. So how do we find the inverse of this function? Let me change colors here. I'm going to change it to purple. Well, I'm going to replace f of x with y. And this is just the same process that we've been doing on day 1 and day 2. And then now what am I going to do? I'm going to switch the x and y. So x equals y cubed. And now my goal is to get y all by itself, which means I need to undo that 3 as an exponent, that exponent. So how do I undo the cube? I'm going to take the cube root. What I do to one side, I have to do to the other. And I'm left with the cube root of x equals y. How would I write this in function notation? F inverse of x equals the cube root of x. And that function looks like this. It's going to kind of start over here and curve and go this way. There's your cube root function. And as you can see, it still passes through the origin, right? That point 0, 0 is a point on both functions. And as you can see, these functions are reflections across the line y equals x, which is a property of inverse functions. So let's move on to the second example and find the inverse of each function below, then graph the functions on the graph provided. So I'm going to go back to my original color here, and let's graph this cubic function right here. I know cubic transformations. This right here, my parent function, we just graphed it. I know this right here, we're going to move this function right 2, and then this will translate the function up 1. So I'm actually going to take what was my origin at 0, 0. I'm going to move it right 2 and up 1. That's like my new origin, if you will. And so my graph is going to do something like this, right? Okay, so there's my graph, and I mean, just there's the general shape, right? So now let's find the inverse of this function. I'm going to replace f of x with y, and I'm going to rewrite everything, x minus 2 cubed plus 1, and then I'm going to switch the x and y, so x equals y minus 2 cubed plus 1. And now our goal is to get y all by itself, so we kind of have to work from the outside in. So the first thing I need to do is subtract 1 from both sides. X minus 1 equals y minus 2 cubed. And now I can't undo anything inside those parentheses until I get rid of that cube. So what do? I'm going to take the cube root of both sides, and that undoes the cube root, or the cube. So I'm left with the cube root of x minus 1 equals y minus 2. That cube root and that cube, they undo each other. Now to get y all by itself, I'm going to add 2 to both sides. And I'm going to go ahead and write this in function notation. f inverse of x equals the cube root of x minus 1, and then plus 2 is outside that radical. So now let's graph this function. We did graph that parent cube root function in the graph above, but now we're going to take, and we know it passed through the origin, right? So we're going to take that origin and we're going to move it right 1 and up 2. So instead of right 2 up 1, I'm going to move it right 1 up 2, and it's going to take this shape right here. It's going to still have the same shape, right? That cube root shape. It goes just like that. And as you can see, another property of inverse functions, this is a reflection across the line y equals x. This is just a rough sketch, but this point right here is 2, 1. This point over here is 1, 2, right? That's a property of inverse functions. Your x and y coordinates switch, right? We switched them in our equation, and because of that, they switch on the graph. Because of that, it's a reflection across the line, y equals x. So let's move on to this last example for the cubic and cube root functions. And this one right here, the function that we're given is actually a cube root function, and we're going to graph it. We know what the parent function looks like. If we were to transform it, this is going to move our function left 2 and down 4. So we're going to take that general shape and we're going to move it. Let's say it crosses through that origin. We're going to move it left 2 and down 1, 2, 3, 4, and it's still going to take that same general shape like that. Okay? And remember, this is a rough sketch, so it doesn't really have to be totally perfect. So now let's find the inverse of this function. What do I do first? I replace f of x with y. So I rewrite it as an equation. Cube root of x plus 2 minus 4. And now I'm going to switch the x and y. X equals the cube root of y plus 2 minus 4. And now my goal is to get y all by itself. What do I do first? Got to work from the outside in. So I'm going to add 4 to both sides. And I get x plus 4 equals cube root of y plus 2. And now I need to undo that cube root. Well, you undo a cube by taking the cube root. You undo a cube root by cubing it. What I do to one side, everything gets cubed on the other side. So x plus 4 cubed, the entire thing got cubed, equals y plus 2. And now to get y all by itself, I'm going to subtract 2 from both sides. And if I write this in function notation, f inverse of x equals x plus 4 cubed minus 2. So we know what that parent cubic function looks like. Let's take that origin, with that point that passes through the origin, and move it left 4 and down 2. Left 4, down 2, and it's going to take this general shape right here. And as you can see, we can see the properties of inverse functions. These are reflections across the line y equals x. This point right here is negative 2, negative 4. This point is negative 4, negative 2. So cubic and cube root functions are inverse functions of one another. Let's move on to our next examples. These are exponential and logarithmic functions. So exponential and logarithmic functions are inverse functions of one another. They undo each other. Let me change colors here. What color do I want to use for this? I'll use dark blue. So they're inverse functions, and we're going to prove that by finding the inverse of this exponential function below. And obviously, we have our natural number as our base, and we're going to graph this function on our coordinate plane. I know that the horizontal asymptote for f of x equals e to the power of x is going to be y equals 0. And I know a key point on my graph is going to be 0, 1. And it's going to go through that point just like this, always increasing. It's going to look just like that. So now let's find the inverse of this function. What process am I going to do? Same process. I'm going to replace f of x with y. y equals e to the power of x, and then I'm going to switch x and y. So x equals e to the power of y. And when I'm trying to get the variable that's in the exponent all by itself, I'm going to have to take the log of both sides. And in this case, since I have a base of e, I'm going to take the natural log of both sides. So the natural log of x equals the natural log of e to the power of y. And I can rewrite what's on the left side of that equal sign as y times the natural log of e. And I'm going to put a little dot there. That's y times the natural log of e. The natural log of e, another property of logarithms, the natural log and the e undo each other, right? Because the natural log of e is just 1. When I have a natural log, I have a base of e. E to the power of 1 is e. Remember, the log is the exponent. So that's basically y times 1. So y equals the natural log of x, and I'm going to rewrite this in function notation. F inverse of x equals the natural log of x. And if I'm going to graph the natural log of x, I know that I have a vertical asymptote, and that vertical asymptote is x equals 0. The key point on my logarithmic function is right there at 1, 0, and it's going to take this shape right here. Whoop! And it's going to look just like that. And so we're proving that these two are inverse functions by undoing them and graphing them on the coordinate plane. You can visually see that they are reflections across the line y equals x, and we can see this key point right here, 0, 1. The x and y switch places. Key point in the logarithmic function is 1, 0. Let's move on to another exponential function below that has some transformations added to it, and let's solve for this. So the first thing I'm going to do is I'm going to graph f of x equals e to the power of x plus 1 minus 3. So we know that that original function has the exponential function. We know it has a horizontal asymptote that's y equals 0. In this case, the transformations applied are left 1, and right here we're moving down 3. So if I'm going to graph this function on the coordinate plane, I know that my horizontal asymptote is going to move down 3 units. So that's y equals -3. And now let's think about that point. The point was 1 above on the the y-axis, right? Here's my x-axis, here's my y-axis. That point is normally 1 unit above the horizontal asymptote. Well, in this case, it's still going to be 1 unit above, but it's going to be left 1. So now it's going to be right here at -1, -2. And it's still going to take this shape right here. We've had no reflections or anything. So this is the graph of f of x. Now let's find the inverse function for this particular graph. So I'm going to follow my same steps. The first thing I'm going to do is replace f of x with y, and I'm just going to rewrite it as an equation. Next step, what do? I switch x and y. X equals e to the power of y plus 1 minus 3. And now the goal is to get y all by itself, which is in the exponent. So first we need to get that term all by itself. So I'm going to add 3 to both sides. We're working our way out to in. So x plus 3 equals e to the power of y plus 1. And then what do I do when my variable is in the exponent? I take the log of both sides. And in this case, I'm going to take the natural log of both sides. So the natural log of x plus 3 equals the natural log of e to the power of y plus 1. So again, I know that my properties of logarithms, I can rewrite this right here as y plus 1 times the natural log of e. And the natural log of e is 1. Y plus 1 times 1 is just y plus 1. So the natural log of x plus 3 equals y plus 1. So when getting y all by itself, I'm just going to subtract 1 from both sides, and I'm going to rewrite this in function notation. F inverse of x equals the natural log of x plus 3 minus 1. I know based on the graphs that I just did, we graphed the logarithmic parent function or natural log parent function and the parent exponential function above, so we could review those key points when we're graphing. So I know that key point, and I'm going to zoom out a little bit, that key point in my logarithmic function, I've got an asymptote at x equals 0, and then that key point is at 1, 0. So right here, the transformations applied to the parent function are left 3, and this is down 1. Left 3 and down 1. So what's going to affect the asymptote? The horizontal translation. So we're going to take that vertical asymptote that was x equals 0, and I'm going to move it left 3 units. So now that horizontal asymptote is at x equals -3. And we're moving down 1. So that key point is normally on my x-axis to the right of that vertical asymptote 1 unit. And in this case, it's going to be down 1 unit, which that point is at -2, -1. And it's going to take this shape right here. It's going to cross over and look something like that. So as you can see, when we've graphed it on this coordinate plane, and I did the best I could with my sketch, but you can see that it is a reflection across the line y equals x, and you can see in those two key points, the x and y values switched places. So let's move on to our last exponential / logarithmic example. And in this case, I have a logarithmic function. And remember, when I have a logarithmic function with no number written down as a base, it's assumed to be 10. So let's go ahead and graph f of x on our coordinate plane. We're just drawing a rough sketch. And we know that the graph of the logarithmic function has a vertical asymptote at x equals 0, and there's a key point on our x-axis to the right of that asymptote. We're going to apply these transformations, and you know what, I'm going to draw this in blue like I've done with the other examples. The transformations applied are left 2 and down 1. So what's going to affect this function right here is the horizontal movement. So instead of my vertical asymptote being at x equals 0 on that y-axis, right, here's my x-axis, here's my y-axis, we're going to move left 2. And there's where the asymptote is going to be, x equals -2. And we're moving down 1 unit, so I know that key point is to the right 1 unit on the x-axis. In this case, we're going to move down 1 unit. So that key point is going to be at -1, -1. And it's going to take this shape right here. Whoop. Just like that, right? Logarithmic function takes that shape. Okay, so now let's algebraically find the inverse function for this function. So what are my steps? I'm going to replace f of x with y. Y equals the log of x plus 2 minus 1. What do? I switch my x and my y. So x equals the log of y plus 2 minus 1. And I want to get the logarithmic portion, right, the log term, all by itself on one side of the equal sign. So I'm going to add 1 to both sides. And I get x plus 1 equals the log of y plus 2. And what I'm going to do is I'm actually going to rewrite it, because this is how I've kind of taught my students to do this. I'm going to rewrite it where the log is on the left of y plus 2 equals x plus 1. And what I'm going to do is, if there's no base, I'm going to write a 10 there, right? Because it's assumed to be a base of 10. I'm going to rewrite this as an exponential, okay? So I'm going to write it as, and this is how I've taught you to do it, 10 to the power of x plus 1 equals y plus 2. So 10 to the power of x plus 1 equals y plus 2. So I can rewrite this logarithmic equation as an exponential equation. And now I can get y all by itself by subtracting 2 from both sides. I'm going to rewrite this in function notation. F inverse of x equals 10 to the power of x plus 1 minus 2. So this is now our exponential function that we're going to graph. I can see because I have the variable is in the exponent. What transformations, and I know that parent exponential function, right? Even though it had a base of e, it's going to take that same general shape and it's going to have the same key point. So what transformations are applied to that parent function? This is going to move it left 1. This is going to move it down 2. I know that vertical movement of down 2 is what's going to affect that horizontal asymptote. So instead of the asymptote being on the x-axis at y equals 0, we're going to move it down 2, and it's going to be y equals -2. And that key point is typically, or it's not typically, it's always on the y-axis, 1 unit above the horizontal asymptote. But because we've moved left 1, it's now going to be 1 unit above that horizontal asymptote, move left 1. So it's going to be right there, which is -1, -1, and it's going to take this general shape. And as you can see, these two functions share that point, because if I switch the x and y, well, if they're the same, right, they're going to share that point. These are reflections across the line y equals x. Let's move on to our last few examples, and these are rational functions. So the inverse of a rational function is typically another rational function. So we're going to find the inverse of each function below. And we're not graphing anything on this. We're just going to work through the process of finding the inverse of each function. So I'm going to zoom in here. I've got f of x equals 1 over x, and I do know that when graphed, this function looks like this, right? Okay, so what do I do? What's my process? I'm going to replace f of x with y, so y equals 1 over x. And now I'm going to switch x and y, and I'm going to replace y with x and x with y. The goal is to get y all by itself. So what do I need to do? I've got to get rid of that denominator first. So to get rid of divided by y, I'm going to multiply by y. What I do to one side, I have to do to the other. And now I get x times y equals 1. And what do I need to do now? Now I need to divide by x. What I do to one side, I have to do to the other, and I get y equals 1 over x. And if I want to write it in function notation, f inverse of x equals 1 over x. And notice that we have the exact same function, okay? We have the exact same function as our parent or 1 over x. The inverse of this function is 1 over x. It's the same function. So let's move on to finding the inverse of each function below. So now we've obviously got some transformations that have been applied to that parent function. Let's see if I get the same thing, because that may happen in some situations. It doesn't always happen. So let's move on. I'm going to algebraically find the inverse of this function. The first thing I'm going to do is replace f of x with y, 3x minus 2 over x plus 4, and then I'm going to switch x and y. So x equals 3 times y minus 2 over y plus 4. And I'm actually going to use the same process that we just did. I've got 3y minus 2 divided by y plus 4. I need to get rid of that denominator, so I'm going to multiply by y plus 4. What I do to one side, I have to do to the other. That gets rid of that, and I'm left with 3y minus 2 equals, and now I need to distribute this x into every term on the inside of those parentheses. So I get xy plus 4x. Remember, the goal is to get y all by itself. So what I'm going to do is I'm going to move this 3y to this side, the left side, and the 4x to the other side. So what do we have here? Actually, why don't I do this? I'm going to subtract xy, and I get 4x equals 3y minus 2 minus xy. Let's move this other term, this minus 2, to the other side since there's no y in that term. So I'm going to add 2 to both sides. And you might be like, why isn't she doing this all in the same step? Well, you can absolutely do that, right? I can move that 2 over and the xy over in the same step. And I'll probably do that in the next example. So what do we do when we get to this point? If my goal is to get y all by itself on one side of the equal sign, what I'm going to do here is factor out a y. A GCF, that's my greatest common factor, which is y. When I factor out a y, I'm left with 3 minus x equals 4x plus 2. And I'm going to keep going, and I'm going to write it over here. So now to get y all by itself, I'm going to divide both sides by 3 minus x. So I get 4x plus 2 divided by 3 minus x equals y. If I write this in function notation, I get f inverse of x equals 4x plus 2 over 3 minus x. Let's move on to our next example. Number 9. And, well, I'm not going to point that out because I haven't done anything. Let's move on to number 9. This is our last example. So f of x equals x plus 2 over x minus 6. What's the first thing I'm going to do? I'm going to replace f of x with y, x plus 2 over x minus 6. And now I'm going to switch x and y. So I get x equals y plus 2 over y minus 6. And we're going to work through using the same process that we've been using. I want to get rid of that denominator. What do? I multiply both sides to get rid of it. Everything gets multiplied by y minus 6. Don't forget, you need to distribute this x into each term inside the parentheses. So I get xy minus 6x equals y plus 2. So what do I do now? In this case, I'm going to move the y to the left. So I'm going to subtract y from both sides. And then I'm going to move, let me just write it out, xy minus 6x minus y equals 2. And now I'm going to add 6x to both sides to get xy minus y equals 6x plus 2. So now on one side of my equal sign, I have only terms that have y in it. When I do that, I can factor out a y as a GCF, and I'm left with x minus 1. To get y all by itself, I'm going to divide both sides by x minus 1. And if I rewrite it in function notation, I get f inverse of x equals 6x plus 2 over x minus 1. And that concludes your day 3 notes over inverse functions. I hope it was helpful.